To be here. My talk's going to be about energy fluxes in some relatively idealized models of ocean circulation. And it's collaborations with Balu Nadiga, who's in Los Alamos, and Stephanie Taylor, who's a graduate student working with me in Montreal. And so basically what I'm going to do is sort of review some of the classic phenomenology of geostrophic turbulence, and then look at how it applies or what it tells me about how energy moves around between scales and between different classes of flow in the ocean. So my ocean models are fairly idealized, but they at least take into account that ocean circulation occurs in a basin geometry. So we have boundaries that are often sort of thrown out in some of the turbulence phenomenology. So I'll do a sort of a quick review of stuff that a lot of you are very familiar with, but some of you might not be. And just to sort of situate my own perspective, I mean, I've been here for a month and enjoyed interacting with mathematicians doing very rigorous stuff. My career has sort of fallen into the gap maybe between some of the more rigorous mathematics and some of the people even less rigorous than me that are doing applications. So, but I'll be I'll be sort of giving a quick description of the way the turbulence community sees energy moving around at larger scales than the scales that Peter was talking about mainly, and then showing how that applies to the ocean. So the starting point is just 2D turbulence. The 2D Navier-Stokes equation, just an advection diffusion equation, and the quantity being advected is related to the velocity field advecting it, in that one's the vorticity of the other. So there are two quadratic invariants associated with the inviscid equations, the kinetic energy and the entropy, which is the square of the vorticity. And the main result is just that the simultaneous conservation of both leads to this inverse energy cascade. Okay, so it's an old argument. It's basically just that nonlinearity spreads out energy in wave number space. So if you have an injection and sort of stirring at a fixed wave number, if you move just a little bit of the energy to larger wave number, where you've moved a correspondingly large amount of entropy to larger wave numbers, so therefore a lot of other energy must be moving backwards in wave number space, so towards larger scales. So slightly more realistic is to include planetary vorticity. So you can think of this as just the part of the Coriolis parameter that's varying with a north-south coordinate y. So the Coriolis parameter is 2 omega sine latitude. And here I'm considering to be a constant plus a term that varies in y. This is this beta term that we've heard a bit about. So you can think of the Coriolis parameter, if you will, as just the vertical component of the vorticity associated with the Earth's solid body rotation. So this introduces a scale called the Rhine scale, just the square root of a velocity divided by beta. And for small scales, this linear term is essentially irrelevant, and we recover 2D turbulence. But for large scales, it's essentially nonlinear. For larger scales, so this Rhine scale sort of is where these two terms are comparable. Vallis and Moutrud pointed out or exploited the anisotropy here. This linear term just involves a zonal derivative, whereas this one is more isotropic. And so the interpretation is that the large scales where the flow is quasi-linear is inside some exclusion zone in Fourier space. So this is a zonal and meridional wave number. So at small scales out here, beta is essentially irrelevant. You expect an inverse cascade in towards this dumbbell shape, and then the energy would sort of work its way around and wind up near the origin, but not at the origin, and also in a very sort of anisotropic way. So you get these jets. So maybe it's a bit of a stretch to claim that something this simple applies to Jupiter, but people do. Okay. So a little bit more realistically, and this is getting closer to what I'll be talking about, is the quasi-geostrophic system. So the quantity being advected around now involves relative vorticity and planetary vorticity, but also this stretching term. Okay, so the z derivatives of the stream function. And for many applications, it turns out that a lot of the energy is really on the first few vertical modes of the system. So a depth average mode and maybe a few vertical modes. So if you think of the Z scale as being set in some sense, say maybe it's related to the height of the tropopause or the depth of the thermocline in the ocean, then that sets a scale called the Rossby radius, which is where these two terms are comparable. Okay, so again, there's an energy and an entropy, but the energy includes potential energy, which would be the Z derivative here, and the entropy includes the stretching term, which are the Z derivatives. And a sort of cartoon for how people envision energy moving around at large scales is that the forcing is at the planetary scale, right? It's the sun, or the winds, and the winds tend to have a much larger scale than the ocean current. So you can think of the forcing as being at large scales, and it tends to project mainly onto these baroclinic modes. So the jargon is that baroclinic means that it depends on Z, and barotropic means that it doesn't. Barotropic is the depth average mode. Okay, so at large scales, the energy and entropy are dominated by potential energy and potential entropy, and they're essentially proportional to one another. So conservation of entropy is no longer a strong constraint on the system, and that's why the energy readily cascades forward. Or you could take that and run with it and come up with a phenomenology suggesting that the energy should cascade forward in wave number space until you reach this deformation scale where relative vorticity is becoming important. And then there are other arguments to suggest that the flow should sort of systematically pump energy into the kz equals 0 wave number, or what I'm calling the barotropic mode. So there's this process called barotropization, where the energy goes into the barotropic mode, and then the phenomenology would want that to fuel an inverse cascade with the barotropic mode acting something like the 2D mode. And of course, this diagram is showing this cascade is going all the way back to the planetary scale, where eventually a large-scale dissipation mechanism is getting rid of it. But of course, what various people have pointed out that it's only going to cascade up to this Rhine scale, and then the cascade slows down, so the energy is going to pile up at a much higher wave number and get taken out by bottom friction here. So various people, this is a very incomplete list, have looked at aspects of this problem. And there's some modifications to this picture. One is just to recognize that the large-scale flow can go baroclinically unstable and kind of directly force scales near the Rossby radius or slightly larger. Maybe, so you don't need a cascade to get energy from the planetary scale to sort of what oceanographers call the mesoscale and meteorologists call the synoptic scale. Instability can do it. And then the cascade would just be maybe a much shorter cascade. People have also looked for this in data, looked for evidence of this barotropic cascade, and found that it's very, very short, or they found, actually what they found they don't think should be interpreted as the barotropic cascade, but it's also very short, and that's just a statement that this Rhine scale and this Rossby radius scale are sort of neighbors. Okay, so one more of these sort of very elementary textbook examples. This one's from Stommel in the 1960s, and it's really the simplest model of ocean circulation. There's no time dependence in it, so there's no turbulence, and in fact, no math, really. I mean, it's just this beta term balancing a wind forcing that's related to the wind stress curl, and a drag term that's model of bottom friction, if you will. So it's a sort of embarrassingly simple model in a sense, but it was very successful because what it explains, so this is meant to be an ocean basin. Think of this as maybe North America over here. This is the Western Atlantic, and this would be Europe over here somewhere. And then I've added a brick wall at say 60 north and 20 north or something like that. And these are the trade winds, the mid-latitude jet, and then winds blowing the other way at high latitudes. The success of this model is that it explained the observations that the Gulf Stream and the strong currents are all on the western side of ocean basins, right, not on the east. And in the context of my talk, what I think is interesting about it is the wind forcing. The winds are essentially wave number one, so they're going to force at the basin scale. They're putting energy into the system at the basin scale. The dissipation is really only relevant where the streamlines are close together, right? So the dissipation is in these boundary layers, which is not a very small scale, but it's smaller than the basin scale. And the only other term in the equation is a constant coefficient linear term. And so this beta term is obviously what's getting the energy from the forcing scale to the dissipation scale. So that's, I mean, often turbulence studies are done in periodic domains. And in a periodic domain, a linear constant coefficient term can scramble the phases in Fourier space, but it can't directly be related to a transfer of energy between scales, whereas in a basin, it clearly can. So that's what motivated Baloo and myself to just sort of revisit this double gyre problem, this time with a little bit of vertical stratification. We have two layers, a top layer and a bottom layer. We just wanted to look at the energetics, keeping in mind that this beta term can move energy around, and ask the question, how does it do that and what is it doing? I also mentioned that the turbulence phenomenology sort of gives a model for how these quasi-zonal jets form, and that was also part of our motivation. This is the zonal velocity associated with my baroclinic stream function, so associated with the difference in velocity between my upper and lower layers. And we saw these sort of quasi-zonal jets that extend all the way across the basin, so this is a particularly nice example of it. And we were looking for a signature of the jets in the energetics, but we never really found one, so I won't say more about that. This was just of interest maybe to oceanographers because there's been a lot of discussion about these jets in the ocean, but they're almost always presented as time averages, whereas this is a snapshot. This is an instantaneous field. But I've capped the values here, so most of the turbulence is occurring in this western boundary region, and I think that's why I'm not seeing a signature of the jets in the overall energetics, because it's just dominated by where the action is, which is the western boundary. Okay, well, so I have a wind forcing, which is, of course, acting on my upper layer, and a bottom drag, which kind of makes sense to put it in the bottom layer. And these equations almost look uncoupled, but the Q1 has a psi 2 in it, and the Q2 has a psi 1 in it. And it's sometimes useful, or at least customary, to think of these equations in terms of this barotropic or depth average mode. So the epsilons are the fractional layer thicknesses. And epsilon 1 is the smaller of the two, so the two add up to 1, but epsilon 2 is like 0.2, and epsilon 2 is maybe 0.8 or something. And you can just think of tau as either temperature at some mid-depth or the height of the interface separating the two layers. So this is what I'm calling the baroclinic stream function and the barotropic stream function.
Is that a rigid lid, by the way?
So it's a rigid lid, yeah. Actually, it's just because it was easier to do the elliptic inversion, there's a free surface, but the external Rossby radius is huge, much bigger than the basin, so it's effectively a rigid lid. Yeah. Okay, but that doesn't change much, really. Okay, so here's my barotropic equation. You recognize this 2D beta plane dynamics, but there's an additional term that involves a Jacobian, so advection of baroclinic vorticity by the baroclinic stream function. So this is the baroclinic flow sort of feeding back onto the barotropic flow, and that's what's going to cause this barotropization process. To form the energy equation, so these are vorticity equations. To form the energy equations, you would multiply by the stream function, so multiply the top one by psi and the bottom by tau. and integrate by parts. Lambda is my deformation radius, so I should have written that differently. Lambda to the minus 2 is my k deformation, kd squared. So kd was this length scale here. Okay, so lambda is the scale where these two terms are equal if I fix the vertical scale. Okay, so it's sort of an nh over f. And there's a pi or something in there as well. Okay, so again, to form the energy equation, I multiplied the top equation by psi and the bottom equation by tau, and just played around with it a little bit. And I want to look at this term. So this is clearly, in the energy equation, I'm going to get a term that goes like this: Jacobian times psi times the barotropic stream function. And so obviously that's describing an exchange of energy between this baroclinic and barotropic modes. This term is, if I multiply this equation by tau, I get a tau times the Jacobian of psi with grad squared tau, which is what I have here. It's a little bit less obvious that this is an exchange between baroclinic and barotropic modes, because you might think that it could also allow for an exchange just between length scales within the baroclinic mode, right? Because there are two baroclinic members in a given triad. But you can in fact argue that, well, in a sense, these are just the same term. I've just moved the position of the psi and the tau, so they integrate to the same thing. But even in a triad by triad basis, you can argue that this should be interpreted as the baroclopization term in the baroclinic equation. So in other words, if I analyze this term, it's going to tell me the length scales or the wave numbers from which this baroclopization process is extracting baroclinic energy. And if I analyze this one, it's going to tell me into which wave numbers that energy is being injected. Okay. Just a few other terms in the equation, a few other points. The forcing, there's an epsilon here, so this is not a tiny number, but it's about a quarter or a 0.2 or something. So most of the forcing projects onto the baroclinic mode, as we've said here in the phenomenology. The bottom drag term got a little complicated just because the bottom vorticity depends on both modes, and then it has to project back onto both modes. So it's a little messy. I'm using a hyperviscosity. And there's some other nonlinear terms in the baroclinic equation. So this one's just an analog to this term that we normally associate with the inverse cascade, but in the baroclinic mode. This term is actually the one that Scott and Wang think they observe in satellite altimetry data, so some of you might be familiar with this. This is the one that Ben was asking about. This is the term that's going to dominate at large scale. So this is the term that people would normally associate with this forward cascade. So when I multiply the whole equation by tau, this just looks like Jacobian of psi with tau squared, which is just the barotropic flow stirring up the potential energy, right? Potential energy would just go like temperature squared. So this is the term that's normally associated with this forward cascade of baroclinic energy. Okay, so I'm going to present things as I'm going to present time average. So I spun up a model to equilibrium and calculated the energy transfers and energy fluxes, and I'll present them as time average values of just the 1D horizontal wave number. Okay. So again, to make the energy equation, I take the vorticity equation and multiply by psi, or in spectral space, I take the Fourier transform of each term, multiply by the Fourier transform of psi and their complex conjugates and real parts and so forth. That gives me the transfer, so I can calculate the transfer associated with the beta term, the Jacobian term, this baroclopization term, and so forth. And I'm going to present them as fluxes, which are just k integrals of the transfers. So my convention is that a negative slope in the flux will correspond to an injection of energy at a particular wave number, and a positive slope corresponds to an extraction. And then an inertial cascade would show up as a region of a constant flux between two sloping regions. Okay, and I'm in a basin, so I'm using sine transform because I want the stream function to go to 0 at the walls, and it's for that reason that my linear constant coefficient term can move energy around in Fourier space. Okay, so this is the fluxes for sort of a reference simulation that uses parameters that oceanographers would be comfortable with. And, well, what do we see? The wind is putting a little bit, and I'm just plotting for the barotropic mode now. The wind's putting in energy near wave number 1, as we expect, okay? But most of the energy is being put in at a slightly higher wave number associated with this barotropization process. So that's also consistent with this phenomenology. What's a little bit different than the phenomenology is the range of wave numbers where this slope is negative, so where energy is being injected into the depth average mode, is roughly the same range of wave numbers where the bottom drag is taking energy out of the system. So in that sense, there's no need for an inverse energy cascade at all, right? I'm forcing and dissipating at the same wave number. There's no reason that the dynamics has to cascade energy upscale to get from one to the other. But the nonlinear term is extracting energy at some slightly higher, slightly smaller scales and transferring it up to slightly larger scales. So there is an inverse energy, not really cascade because the inertial range is just a point here, right? So the Rhine scale where so my point is that, so there's this nonlinear cascade, but it's not taking the energy from a source to a sink. Rather, it seems to be compensated to some extent by an acceleration in this forward transfer of energy associated with the beta term. So there seems to be a looping around of energy in Fourier space, if you will. Okay. The next slide, I'm going to look at this curve again, but it's going to be blue. So here it is. So this is this term that I mentioned earlier. It's just showing the range of wave numbers into which this barotropization process is injecting energy. And I guess not a big deal, but it's just slightly different than the range of wave numbers out of which this energy is being extracted. Okay, so the barotropization process is extracting energy out of wave numbers comparable to this Rossby radius wave number, as you would expect, and it putting them into slightly larger scales. So I did these simulations for a large range of drag coefficients, a large range of forcing scales, and forcing amplitudes, and a large range of deformation radii. And I'll just show you the results for the different drag coefficients. So here I've just sort of isolated the double cascade, or what I'm calling this double cascade. So this beta transfer that's taking energy forward, and the nonlinear term that's taking it back. So again, this is for the barotropic mode only. The range is, so what is this? Magenta is the one that we just looked at. That's my reference simulation. And I went from 1/8 the drag coefficient to 8 times the drag coefficient here. And you can see that as I decrease the drag coefficient, what I'm calling this double cascade is accelerating. It's getting much stronger. Also, you can see here that this correspondence in scale between the scale at which barotropization is putting energy into the barotropic mode and the scale at which the Rayleigh damping basically is taking it out seems fairly generic. It's not perfect, but it seems to work over a wide range of scales. So that's also true for a large range of forcing amplitudes that I considered, and a large range of Rossby radii. That just seems to be a fairly generic result. This is just showing the wave numbers from which barocloprization is extracting energy out of the baroclinic mode and into which it's injecting it. And this slight offset is exacerbated for weak damping and is not, it goes to 0 basically for stronger damping. This has to do with various terms in the baroclinic equation, but I won't go into it in detail. So here I'm just trying to, for all of my simulations, just quantify this correspondence and scale between the barocloprization input and the drag. So I've just defined a injection-weighted wave number and similarly a drag-weighted wave number and just plotted them for all my different Rossby radii, my different forcings, and my different drag coefficients. And it's not perfect, but they line up more or less. So in other words, this correspondence seems to be generic over the range of parameters that oceanographers would consider reasonable. And so why? So my explanation is not complicated. Basically, this is the term that's doing the transfer. This is the term that's injecting energy into my barotropic mode. And what I want to argue is just that all else being equal, the transfer of energy into a particular Fourier component depends on the amplitude of the energy that's already in that Fourier component, or the amplitude of that Fourier component, right? So there's a tendency for the system, there's sort of a preference for the system to want to add energy to the modes that already have energy, right? In the same way that sometimes the economy wants to put money into the pockets of those who already have it, right? Okay, so it's the same idea. And so maybe that would not be the case if I had a large separation between my Rossby radius scale and my Rhine scale, because then you might argue if the wave number associated with the energy containing psi field was very different than the wave numbers associated with these taus, then you might argue that the disconnect in wave number would mean that there are fewer triads, or that the triads are less resonant and so forth. And so you might not get this. But the fact that the Rhine scale and the Rossby radius are so close, they live down the street from one another, and that's true for the atmosphere and the ocean, I think, means that the transfer is going to be preferentially into the modes where the energy is already resident. Okay, so I just want to revisit my cartoon here, and this is showing an eddy mean decomposition, this time for the baroclinic cascade. So for this part of the cascade, my deformation wave number is about here, so all the action's really in this part. And the dark red curve are the terms that only involve time average quantities. Okay, so there's no turbulence except that, or there's no direct effect of turbulence, right? In fact, most of it's just the beta term associated with the time average flow. So the energy is getting from the basin scale to what oceanographers call the mesoscale without having anything to do with either baroclinic instability or cascading turbulence. It's just the solution, just sort of like the Stommel gyre problem that I showed. The blue curve is all the terms involving eddies, and in this case I'm actually getting an inverse cascade associated with the eddies, right, in the baroclinic mode. But it turns out that inverse cascade is a little bit, is mainly associated with this term here. It's just an eddy forcing of the mean flow, so it's an eddy mean flow interaction. So the eddies are actually forcing the large-scale baroclinic mean flow, if you will. And it's in fact this term that's usually associated with, or actually this one is the one that's usually associated with this forward cascade. That's shown here, and it's confined to scales essentially between the Rhine scale and the Rossby radius, again, as you might expect, because the Rhine scale, this term it becomes energetic at around this scale, so that's where it does its stirring and moves energy forward. Okay, so it's a mistake to think of this large-scale transfers in terms of the kind of classic turbulence phenomenology. Okay, so then I also mentioned that this arrow might be a little bit more like this, and then that this dissipation is kind of right here, right? So it goes from here to there and out, right? But there's, and also the barochopization process can also include mean-only terms and eddy mean flow as well as the eddy-eddy term. So, but there's no neat story there. And then, especially in the low damping limit, even though I get this injection in and the energy being taken out right at the same time, there's nonetheless a nonlinear inverse cascade and a forward beta cascade. And in the limit, in the low drag limit, where this, we call it a double cascade, is particularly large, that is associated with eddy-only terms. Basically, it's just the turbulence doing it. And I don't have a good physical picture. I have one in my mind, but I can't quite prove it. But what I'm thinking is basically where the Gulf Stream turns out to sea and wiggles around, there's a lot of turbulence near this western boundary layer. So not in the western boundary, but near the western boundary. And so there you might expect the turbulence phenomenology to apply. But the eddies grow, and they slam into the western boundary layer and just get sheared out into longer filaments, which would be this sort of beta cascade. So you get a sort of but then the filaments get spit out in the Gulf Stream extension again, and the cycle starts over. So that's a very hand-wavy. But so the last few minutes of my talk, I want to talk about this trickling down of energy. So the solid arrows are meant to be energy and the dashed ones are meant to be entropy, but this trickling down of energy to small scale. So this is sort of more in the range of scales that was kind of more relevant to Peter's talk, I think. So the cascade to small scales is mainly thought to be related to unbalanced motion. So, and in particular, near inertial motion is the slowest of the fast waves, right? So you think of inertia gravity waves, they exist between the Coriolis frequency and the buoyancy frequency, but the buoyancy frequency is the larger of the two. So the near inertial waves, first of all, they have large horizontal scales, so they can interact easily with the geostrophic flow, which has large horizontal scales. And they have the lowest of the high frequencies. So there's a possibility for frequency matching. And the claim that I want to make is that if you force them directly, right, remember that the winds have high frequency components, and the sun, you know, one hemisphere is day and the other's night, and the world's spinning. So the forcing inherently includes high frequency forcing, and so you know, like in Peter's talk, he was carefully balancing his flow, and then finding even when he carefully balanced, there was a small amount of excitation of unbalanced flow, and then some of that trickled down, and if you have a big enough computer and large enough resolution, you eventually saw it, or he eventually saw it in his spectra. But the amount of that energy was small compared to the overall geostrophic energy. So you know, it looks big if you're looking at the high wave numbers, but if you don't care about the high wave numbers, you're just looking at the general circulation, the amount of unbalanced energy, it's relatively small. So in realistic regimes, the unbalanced flow is small unless it's externally forced, is my claim. And there's sort of two arguments for that. One is that this spontaneous generation mechanism, this sort of tendency for the balanced flow to sort of create unbalanced motion, is very, very small, as Jacques has pointed out. So it's exponentially small in the Rossby number, but the Rossby number is not that small. Okay, so we could argue about what it is, whether it's 2 or 0.2, certainly in regions of the flow, such as the Gulf Stream and so forth, the Rossby number is not that small. So there'll be a little bit of generation, but not that much. And then another problem is that anytime you get any of this unbalanced energy there, as Peter mentioned, it gets cascaded rapidly downscale. So even if the Rossby number is locally big enough to spin off some inertia gravity waves, those gravity waves are quickly swept away, swept downscale, so that they're not interacting with, so the saturation level tends to be fairly low. But if you go around and put a current meter in the ocean, you see inertia gravity waves everywhere. Something like 10 to 20% of the kinetic energy is in near inertial modes compared to geostrophic modes. And sort of my ill-advised question at the end of Peter's talk was just pointing out that a lot of that energy is actually in the large scales, right? It's in the large scales. And so my claim then is that there's a growth rate or a tendency for the balanced flow to dump energy into unbalanced motion. That depends strongly on the Rossby number. And then the transfer, at equilibrium, the transfer of energy from balance to unbalance is going to depend on this sort of growth rate or coefficient that depends on the Rossby number of the balance flow, but also on the background level of unbalanced energy. Just like I said before, the transfer into a mode depends on the amplitude of the energy that's already there. Okay, and so I wanted to look at that. This is with my student Stephanie, and so we're looking at a primitive equation model now, and it's a channel, and it's a southern hemisphere. So this is the polar part of the channel and the equatorial part. And it's forced by a wind stress, which is 0 on the edges and kind of goes up to, it's eastward everywhere. It goes up to a maximum in the middle, and it's 0 on the southern end of the channel. And the reason things are kind of going up here is we have a ridge in the middle. And then superimposed on this essentially geostrophic flow, we forced with a uniform wind, so uniform in space, but high frequency in time. So just a stochastic high frequency forcing in time that excites inertial oscillations. And it excites them at large scales. How do I turn? It's a movie, but here it is. And this is a case where I forced sort of particularly hard. The high frequency forcing is particularly strong. But you see these inertial oscillations superimpose on the geostrophic flow. And then the question is, are they interacting with it in any real way? So what I'm doing is basically just pumping up the inertial energy. And I want to see if when I add a bunch of inertial energy there, if it can extract energy out of this geostrophic part of the flow. So this is just showing spectra as a function of frequency for kinetic energy in the upper part of this water column. And if I don't force the high frequencies, I don't get any response to speak of at the high frequencies. So the little bit here is probably just an artifact of the windowing that we had to do in the analysis. But if I force it a little bit, well, I get a little bit of high frequency motion. And if I force it a lot, that's what I was showing you, you get a lot. And so what we're doing is trying to see if this high frequency stuff is influencing the low frequency energy in any appreciable way. And when you look on a log-log plot, it's not obvious. But if I plot it, the high frequency part of the energy, so the energy associated with the high frequency motion, and the energy associated with the low frequency motion is the solid lines. The one that I was showing you is magenta, so it actually had more, right at the surface layer, there was actually more high frequency than low frequency energy. But you can see as I force the high frequencies directly, you get more high frequency motion as you would expect. But in this case, anyway, you get less low frequency energy throughout the water column, right? So that's what we were expecting, and that's what we found for this simulation. If instead my base state forcing were a little bit weaker, so my the Rossby number associated with the geostrophic flow were a little bit weaker, so this tendency for spontaneous imbalance were much weaker, right? Because it goes, it drops off fast with the Rossby number, and in that case, I forced the high frequency, so I got a little more high frequency motion, but actually some of that leaked in to force the low frequencies rather than drain them. Okay, so I mean, obviously that has to be the case in the limit where my base state, my geostrophic base state is 0, and I have high frequency force, and it can only add to it. But my point is that if the forcing is strong enough, then, if the Rossby number is strong enough, then this will be an appreciable dissipation mechanism. And I think I'll just end with this, just a little thought experiment. If you imagine the bottom, so in other words, whether or not this mechanism is important in the actual ocean is going to depend just on the luck of the draw, on how strong the bottom drag is and what parameter range we happen to be in, because things are very sensitive to the Rossby number, so it depends on exactly what the Rossby number is. But if you consider somehow artificially just turning off the bottom drag, then what's going to happen if you're lowering the bottom drag? Then there's no longer the main dissipation mechanism is gone. So for the same forcing, you're going to get more total energy. So the energy is going to increase. Well, the Rossby number depends on U over FL, or is U over FL. So as the energy increases, U increases, but L might also increase, right? But if you take L, the relevant L, to be the Rhine scale, that's where all the energy piles up. That increases like the square root of U. So I conclude that the Rossby number increases like the square root of U. This is an F. I don't know why you can't see it, but as you drop off the drag. So in other words, if you imagine lowering the bottom drag, eventually the Rossby number is going to grow until it's large enough to allow for this sort of transfer to happen. So my argument is that this balance to unbalance transfers might be a significant player in the overall energetics of the ocean, but only if the Rossby number is locally large and only, only to the extent that that there's a significant amount of resident unbalanced energy in the system, and there is, and the way I think it gets there is not loss of balance per se, but just external forcing. So I'll leave it at that.
So, questions? Jack, the experiments where you shake the surface of the ocean, it doesn't seem to be terribly convincing. I mean, you don't seem to lose much balanced energy in spite of shaking pretty far. Is that fair, or?
Well, yeah, maybe. I mean, shake it pretty. Yeah. You're not losing a lot, but you're losing.
How much energy do you have in the inertial part of the spectrum compared to the balanced part?
Well, I mean, it's here, right? So there's, except for the purple one right at the top, there's more energy in the balance flow everywhere.
Yeah, I mean, the real ocean is more, as you said, 10%, maybe less.
Right. Okay. So that's the blue curve. Yeah. Yeah.
Question?
Yeah.
This is only part I understood, I suppose. You said about bottom drag in the end,
Yeah.
because that's where you get major energy dissipation in ocean.
I mean, I guess the reason I started thinking about this is, 10 years ago or 20, most oceanographers were convinced that the only credible sink for energy in the ocean, mechanical energy, was bottom drag. So they would just tune the bottom drag coefficients until they get an answer that they like. But the bottom boundary layer is on the bottom of the ocean, so it's hard to observe, and it's kind of unconstrained. So I've always been looking for other ways to balance the energy budget.
Story I heard about. So
Okay,
that's why I'm,
Okay, so this is one. Another is top drag, right? When stress, the rate at which the wind puts momentum into the ocean depends on the surface ocean velocity, and that translates to a drag that can remove energy from the surface energy, and actually that's been shown to account for like a third of the energy dissipation, if you will.
hold on. So 1/3 is still inside.
Well, I mean, people will quibble about the numbers, right?
Subject, but I
Yeah.
think this is all story. In order to explain thermal hairline circulation, the certain Jeffrey said beginning of last century
Yeah.
we need very high AD diffusivity.
Okay, no, that's
a
something.
long
No, that's
story.
not really what I'm talking about. That's
Yeah,
something
but
else. That's something else. There's
That's a different time scale. So that's
well, it's a different time scale. It's an argument that involves energetic, but it's a different one. They're saying to get the deep water in the ocean back to the surface, you have to mix it.
Something like that.
Okay, and to mix it, you need a mixing coefficient there's the idea that the buoyancy circulation is forced at the surface by buoyancy, and that can't put energy in the high Reynolds number limit. But I think the resolution to that, and also another thing that's probably more relevant than the stuff that I discussed, is flow over rough topography. So geostrophic flow over rough topography can excite fast motion, right? Can directly excite. So you can think of that as a loss of balance mechanism, if you want. The geostrophic flow over the rough topography excites waves, and the waves go up and break.
Okay, but bottom line, you're not resolving this kind of circulation.
No, not in this model. No. Yeah.
What questions? Yes.
So to what extent do you think your barotropic double cascade, this kind of balancing nonlinear and the beta term, is just stirring of PV around the whole gyre by the gyre circulation?
I don't know. What does that mean?
I mean,
yeah.
You know, you just take filaments of PV round, and you would interpret that as advection, but you would also have a beta term, wouldn't you, as a result?
I guess so. I mean, I suppose, you know, you could say if I just grouped them together, you wouldn't see anything. So, because they would cancel. I think it's different. I think somehow the dynamics does want to do an inverse cascade in the interior, right? You know, I mean, if you look at a little patch of ocean isolated from the boundaries, you would sort of imagine it behaving as if it were on an infinite plane somehow. But it's cascading energy up to large scales. Eventually, that makes coherent vortices, or eddies, we call them, that'll go and hit the boundary layer. And when they hit the boundary layer, the beta term, and I didn't show it, but also just the time mean barotropic vorticity, so the boundary current will just strip it out. That's what I think is going on.
So in the first half of your talk, you used a sort of idealized model to see how the energy transfer from baroclinic to barotropic, like with all these
Right.
And then there's a clear sign, like definite sign that I think the baroclinic is losing energy and barotropic.
Sure.
And then mathematically, just one term, like with a J. And can you see why mathematically that's the case?
Why it has to go that way?
That gives you a definite sign, right?
Yeah, well, so why, yeah. There is an argument for that, and it's just not on the top of my head right now. So, yeah.
It's in Rick Salmon's book.
It's in Rick Salmon's book, yeah.
There is an argument. Yeah.
Yeah.
I can't remember exactly.
Yeah.
But
Yeah. It's
Yes, there's an upscale the vertical as well as the horizontal.
Yeah, there's an upscale cascade that tends to go, including KZ. It just wants to wind up in the large horizontal KZ equals 0.
There's a question back here.
So you showed right at the beginning that you have some very weak zonal depth
Yeah.
in the eastern
Sure.
domain.
Uh-huh.
Do you think if you cut out that part of your domain and looked at the spectrum, you'd see
Maybe,
a dumbbell?
maybe. I was trying to do, an energy budget for the whole domain, so I wanted to do the whole domain. But that's probably something that might be useful, right? And that's what the people looking at data did, of course, right? They went around and drew boxes, and yeah.
Okay, well, I think we're getting to that stage of the afternoon where nobody can remember any of the others.
Okay.
There's a reception in 10 minutes, so thank our speaker and all the other speakers.